Now let's look at what this plays out as. So here's a figure showing a potential, 1 over r squared potential, and showing the energy levels. And this is actually for z equals 2. So this would be a helium nucleus that's been ionized. So this is He plus. We have a +2 nuclear charge and a single electron around that helium nucleus. So the energy level goes like minus z squared RH 1 over n squared, and the z squared here is 4 because we have helium. And so the energy, the lowest energy level, which is right over there on the right of my writing here, is minus 4 Rydbergs, and we go up from there. So the quantum numbers here are 1, 2, 3, 4, 5, 6. So we're showing the first 6 energy levels for this solution. And the thing to note here is this 1 over n squared dependence makes for an incredibly stacked set of states. The gap between the first and the second state is enormous. In fact, it's 3/4 of the Rydberg constant for the problem. So z squared times the Rydberg problem. In this case, it's 3 RH. So it's 330,000 wave numbers. It's an enormous, enormous, enormous value. The gap between the second and the third is considerably smaller, and then the fourth, smaller yet. 5, 6, we're almost all the way out. And there's an infinite number of states between that n equals 6 and the 0. So there's a huge number of states that are packed in there that have very, very small spacings between them as we get to high principal quantum number. And those will come back. We'll talk about those again in the future. But that's the characteristic here. Now the energy levels have gone to being, instead of when we started in the particle in the box, the way the energy levels were getting farther and farther apart quadratically. We did the simple harmonic oscillator, and the energy levels were were evenly spaced because space is getting larger as we go up in quantum number. We looked at the Morse potential, where the energy levels start to get closer together by a little bit because it's no longer harmonic, and as the bond breaks, it pulls apart even more. Well, here, this 1 over r function, and man, the states get really, really, really close together, and we'll discuss that why in just a second. The other thing we've got here is these excitations. The energy differences go like z squared times the appropriate, times the Rydberg constant, so that term there is going to be 4RH, and then the lower energy is going to be 1 over the initial quantum number squared. In this case, that's 1, and then we have minus 1 over the final number squared. So for example, the first energy difference is z squared times RH times 1 minus 1/4, or 3/4. So that first gap there, that first delta E to the left of those green arrows, is 3/4 of 4 Rydbergs, or 3 Rydbergs, and you can see that right on the graph. We go from -1 to -4, the difference is 3 Rydbergs. Those differences are going to be the differences we see when we do spectroscopy, and we'll talk about that in just a second. Now, the other thing, though, that before we get to the energy gaps anymore, is just what these things look like. So what the appearance of the radial wave functions we'll deal with a little bit more in the next conversation. But I want to look at just what we expect here. So the first state is going to have no nodes. It turns out it's going to have kind of a cusp in the middle there. The negative r part of this graph, by the way, it doesn't really exist. R goes from 0 to plus infinity. Should point that out. The angle would be responsible. This would basically be turning 180 degrees in phi, and maybe a change in theta as well, depending on where we are. But if theta is pi over 2, this is just turning phi by pi, by 180 degrees. But it's really useful to put the minus r on these diagrams to look at things. But I should point that out. R really goes from 0 to plus infinity. So because the energy goes to minus infinity, the potential energy there at r equals 0, we actually have this little kind of cusp in the wave function when we include the negative r part of the wave function for visualization purposes. So we don't expect any nodes. We expect the function to decay away towards zero in some fashion, and in fact it looks like kind of like this purple function I've shown here. The wavelength has got something to do with the distance between zero and that classical turning point where energy equals the potential energy there. So that lambda is roughly the wavelength. We go up to the second level here, and there's going to be a node. And so we're going to go from some value down through that node to a negative value and then work our way back up toward zero as we get into the classically forbidden region there, just like with a simple harmonic oscillator. But you notice that the wavelength has barely gotten it's almost the same, really, as the wavelength in the first system as I drew it. And so this is why, part of why the energy levels get so much closer together, because as the space available to the solutions is expanding enormously quickly there, and so the separation between the nodes doesn't really get all that much closer together as I go up in this space, and so they stack together. And the same thing goes for the third state. Now the separation is something like what I've drawn here. There are details because of the spherical Laplacian that the actual quantitative value is a little different here. But the key is that the space is opening up so wildly that the curvature, the curviness of the wave function, as I add in nodes and go to higher energy, I'm always going to go to higher energy as I add in nodes, but it doesn't, the wavelength doesn't get dramatically shorter. And remember, for the particle in the box, if I double the number of nodes, I cut the wavelength in two. And since energy goes like momentum squared, that means that I'm going quadratically up in energy. And here, nothing much happens to the wavelength. It just barely, if anything, gets shorter. And so the energy levels don't really go up all that much, and I can pack a whole lot in, especially as I get into this area where the potential is sort of zipping off and is almost flat, a very, very shallow floodplain basically there, and I can put in very, very closely packed energy levels. And so that's where our intuition, our ability to sort of work through what must be going on here can help a lot. And we'll go into much more detail about the physical appearance of those radial wave functions in the next video, but that's basically what they're going to look like. Now, to turn back to these energy level spacings here, if I shine light on the system, it turns out that I always have to go from an initial to a final state. That's always for sure. But now the selection rule is anything goes. So I can go from any initial state to any final state. But because this enormously strong difference between the first step, let's say the 1 to 2 here, and all the rest, the actual frequency, the actual wave number, those energy difference, groups into characteristic bands that are completely determined by that initial quantum number. So when the initial quantum number equals 1, I get a whole pile of energy differences that start at 3/4 of the maximum energy that I'll get, and proceed up to the full amount of energy that I'll get. Because 1 to 2 is 3/4 of the difference between, in this case it's from -1 to -4, and that's 3/4 of the way from 0 to -4, which is where I get, if I get n equals infinity. So I gather all of each of those comes into a band structure. So if we look in wave number space, what we'll see is this very, very tight bunching of the lines. If you look at how those things play out, the first step is the smallest wave number, and so it's over on the left. The next step is considerably larger, and then very quickly, as I work my way up, the rest all gather together, and they come up to what we call a band head. And those things are labeled, typically alpha, beta, gamma, delta, etc., and then where they all bunch together there, we call that a band head. And it's a very sharp distinction from just, it's almost diffuse to the left-hand side, where any old energy will work out, and then all of a sudden nothing. I don't get really much more absorption at all. Actually, I'm ionizing the darn thing when I do go to higher energy. And so as an example One of the most famous series is called the Lyman series, and Lyman alpha is when, so Lyman for hydrogen, so we have Z equals 1, and Lyman is when the initial energy, the initial quantum number is 1. So the Lyman alpha series starts at 3/4 of 1 Rydberg, or about 80,000 wave numbers, and it will end where Ni is equal to 1 and Nf is equal to infinity. It will end there at 1 Rydberg, 100,000 wave numbers. So you'll get a bunch of lines that go from about 80,000 wave numbers to 100,000 wave numbers. You can't see that, so that's in the ultraviolet. Lyman alpha is an ultraviolet line, but it's a very, very, very famous one. That's basically how it plays out. We know what the energy levels look like within the potential. We can figure out what the wave functions look like, and then we know even about the spectroscopy that you get this characteristic bunchiness, sharp atomic lines, but they all kind of bundle together in this incredibly characteristic way, and that can absolutely identify which atom you're looking at, because that spacing is completely characteristic of a given atom if you have a single electron atom.